I don't know. Hang on. Okay, let's see. That's something. It's going to be here. Oh my goodness. Can we hear you now? Is anyone on? No, I'm just recording it. Okay. Sure. Okay, now. Oh, it's transcribing. Okay. Okay, that's good. Now, let's see. Is it heard? Yes, if we try again. Okay, can we hear? Okay.
There you go.
Yeah, but I'm a bit scared that the audio is going to be like all echoey. So like it's just going to be like death to watch after.
Well, it won't be if it's.
No, but like I've just muted that, so I don't even know if like join. Do you want to join the meeting and then like
Yeah, okay.
I'll see if yeah.
On Teams here?
Yeah. No. Okay. What's the thing? Oh, you don't have your computer. Okay, fair enough. Oh, damn. You know, let's see if I can. Oh, wait. Okay, I think the mic's working. I don't know where the mic's coming from. If I turn on this, it can't hear me. Maybe it can. Can you hear me? No, it's really quiet. Okay. Okay, can you hear me? Wait, hold on. I have no idea. There's only. Wait, can you see? Then if I talk now, but then like I can't hear myself talk. So like, if I turn this on, if you can hear me, yeah, it's like echoed.
So I think it's doing that because it hears it out of there. That gets picked up the microphone, covers the loop.
Okay, well I'm gonna go over here. How is it? Is it better? Okay. So I think we're good. just mute it. Cool. Okay. Now. Welcome. We got the tech sorted. So, feel free to have more chocolates. If anyone wants more caramel, go on, Margar's here. There looks over there. Cool. And if everyone can scan the QR code, that'd be amazing. So we can have more revision sessions and chocolates and events. Okay, now let me try share the screen. Share video. No. Okay. Damn. Share whiteboard. No. Share PowerPoint. No. Again, you know what? It's okay. This is just doing this. And the QR code is still there. Can I like share my screen? Yeah, share screen. There we go. So if I like go in there. Perfect. Okay. Cool. Everyone can see my screen. I'm gonna pin myself. Jeez. Can I? Okay, so I think I'm good. Oh no, because the audio's coming out of this, so it won't be bad. Okay. Does anyone like have any questions about like general topics that they want to go over before anything? Circular motion. I heard that one. Where's it? Okay, I want to write this myself up here. Red. Okay, so. Circular motion. Don't worry, don't need to read that. That's for myself. It's not for you guys. Anything else? Any other topics? Center mass. Okay. I think I've already got some questions like this in here, so that's good. Anything else? No, inertia? Cool. Moment of inertia. That's a really annoying one. I think my questions are covering these, so I'm good. I'm happy. Anything else? Just the whole term so far. Yeah, don't worry. Think of what did I see on someone's like listen to something was like, oh, on the Instagram I saw someone was like, I haven't watched a single lecture this term, and I'm like, well, that was great. At least you're honest, you know. A lot of people are like, no, what do you mean I'm on top of it? In reality, like they're lying to themselves. Like they're all like behind. You know, I mean, I'm like what, like 2 weeks behind one of my courses, so.
I'm 2 weeks behind one of mine as well.
I think I'm 2 weeks behind on all of mine, so that's what Flex Week is for, guys. Okay, so first question. Now, let me see if I can. What time is it? Okay, we're good for time and joining stuff. You can join. Okay, cool. The question says a force of 15 newtons, 15.5 newtons, is pushing block 1 in figure 1, which is this one. Block 1 has mass 4.13, so that's 4.13 kilograms. Let me see if I can make a thinner pen. Okay. And block 2 has 19.37 kilograms. So that force here is 15.5 newtons. And I don't know why it says J, because normally J means the y-axis, but we just, the diagram says it's pushing that way. So I think they're just calling J X instead of Y. But, it's okay. So the diagram tells us what we need. Friction is negligible. That's good for us. Was the acceleration of block 1. So we know that, okay, so we'll do this. Can everyone see that on the board? Somewhat. If I just turn the color inside out, settings. Okay, is that better for everyone's eyes? Yeah. Okay. Cool. Okay. Yeah. So we know Newton's law. F is equal to ma. What's that? Number 2. the sequel. And then, so we know that's 15.5 is equal to the mass. Now, since the force is acting on both objects, what mass are we going to use? Yeah, exactly, yeah. I mean, yeah, both of them. So that's good because the force is acting on both. So it would make sense, what's the acceleration of block 1? Since the blocks are together, the acceleration of block 1 is the same as block 2. So, whoa. Okay, so we got 4.13 plus 19.37 A. Cool. And then we can do 15.5 over that, I'm just going to call this M to save a bit of time. Does everyone mind if I just call that big number there M and just put it on the bottom? All good? Not scaring anyone? Cool. Okay, and then when you chuck that in the calculator, that should give you 0.66. And the reason, it might give you a very long number, but like we were talking about before, the reason why we do that is because the most amount of, we got 3 sig figs in our question, because we got 15 point, the least amount of sig figs we have is 3. This one here is 4. Oh, why is that pen bad? Okay, this one here is 4, but this one here and the others are 3. And then the other one's 3 as well. So that's what we want to use. 3 sig figs and 0.66. And then in Moodle, it'll give you the units. But if it doesn't, we want J because it's in the same direction as the force, acceleration. And then units for acceleration is, we all know and love, meters per second to the -2. I wrote it like that. You can also write it like this. We don't really mind. It kind of makes, it's the same thing. Any questions so far? Just pretty easy start. Not too bad. Cool. That's just Newton's second law, I think. What does block 1? What force does block 1 push on block 2? Now, this one.
Does the acceleration of block 1 also consider the mass of block? Or am I?
Oh, okay. The reason why, so the question asked was why is the acceleration of block 1 considered 2 as well? Is because the blocks, they're together, right? They're going to be, moving at the same time, moving at the same rate. So the acceleration of block 1 is the same as the acceleration of block 2.
Oh, so it's like a trick.
Kind of. Yeah, what is the acceleration of block 1? Yeah, kind of. It's really the acceleration of the whole system. And if you just look at block 1, it's just going to be the same acceleration as block 2. It's kind of I don't know, moving, I don't know if you guys can see, moving these things together. So moving these things together, obviously, this is going to have the same velocity or acceleration, whatever, as that. Does that make any sense? Cool. Okay, what is a force? What force does block 1 push block 2 with? Now, now this is a bit of a weird one, so I'm just going to write it out and explain myself. I don't like this. There we go, back to that one. M1, M2, A1. Now, the reason why I have that is because the whole system has acceleration A1, or A, and it's pushing block 2. So we want to find, what's the force on block 2. So we're going to use the mass of block 2, because that's what kind of is, the force is acting on. Or ask what force is acting on block 2. Or the force on 1, force by 1 on 2. Is that making sense? Yeah? Cool. Okay, so which is going to be, mass of block 2 we said was 19.37 times by 0.66. Yes? Which, we get our calculators, we work out to be 12.8. And then the direction is already there, but just in case, newtons. And again, 3 sig figs, that's what the question was. Any questions? Good? Yes? Everyone's not looking confused. Okay, I'm happy. Now, Okay, part C is what force does block 2 push block 1 with? Now, who remembers Newton's third law? Is it third law? Yes, third law. What was that, sorry?
Every reaction.
Exactly. So if we have, just jump over here, these two blocks together, if this one's pushing that way with a certain force, which we found, previous question, Newton's third law says that, well, block 2 on block 1 is just going to be the same magnitude in opposite direction. Equal and opposite. Is that making sense? Cool. So we basically did it in the previous question. I'm going to write it, no, other way around. On 1 by 2. Force on block 1 by block 2. Now that's just going to be same magnitude, but opposite direction. So I'm going to put a negative sign in the front, and then, is that making sense? That's because of Newton's third law. My handwriting's horrible. There we go. Is that making sense? Cool. Okay, we're sweet for that question. Next question. Someone did mention inclined plane stuff, so I'm gonna go ahead and do that. A block with mass 2.02 kilos is placed at the top of the hinge. Okay, wait, hang on. I'll just start again. Okay. A block with mass 2.02 kilos is placed at the top of a hinged inclined plane with a length 1.62 meters. The angle of the plane makes it horizontally is slowly increased. The block starts to slide when theta is equal to 22.3 degrees. The coefficient of kinetic friction is mu k equals 0.339. Now, part 1. What is the coefficient of static friction between the block and the plane? Now, who remembers the lab from week 2? Maybe week 2. Yeah, the force and inclined plane. Yeah. What was does anyone remember the formula for what mu s is equal to? Yeah, exactly. Tan theta. And does anyone want me to go over the derivation of that? It was in your pre-work, I think. Does anyone want me to go over it again? They can if they want, honestly. Welcome, hello, come in. Okay, so we're all good for the derivation of that? I think, yeah, cool. Okay, I don't know if everything's in your formula sheet. Probably is. Oh, it's also open book, so I think you're fine. Good formula. Is it open book? The lab and week test in week 7. Wait, is it?
No.
Damn it. I don't suck. Okay, because I did this course online because it was kind of COVID times. Oh, welcome. Yeah, revision session. Yeah. Welcome. Yeah, I did this course online in 2022. So yeah, it was all online, and also I had a final exam. You guys don't, so kind of makes me jealous. But yeah, okay. No, just not 1A.
Higher special 1B does. So if you're a physics major, then you have to take higher special 1B.
You don't have to take it.
Sorry?
You don't have to take it. I think it's just higher 1A and 1B.
Advanced physics.
Oh, I didn't.
Yeah, because you're a math major.
What was that? Yeah,
Well,
but
we're recording it.
yeah, it's not live. It's just recorded. So I think you guys can look back at it. So we're all good. Now that question was pretty easy. Okay, wait, hang on. Let me just finish this off. Tan of 22.3 degrees should get you there. I think, does anyone want to put in the calculator just to confirm? Should be 2. No, hang on, wait, 0.41. Does anyone have a calculator on them? Okay, cool. Do you want to put in tan 22.3? Remember degrees mode. Remember the mode you're in. Don't make that mistake. Okay, yeah, that's good. 413. Yeah, okay. And we just rounded it because, again, 3 sig figs is the least, so. Cool. Next question. The angle is now increased 25.6. Now, when I'm doing questions, I like to, write down all my like constants that I have. So I'm just, and this is a force question, so it'll be useful to have the mass. So we have mass 2.02 kilograms. Theta is now 25.6. We have mu k is equal to 0.339. And that's it. Okay. And obviously G we know is 9.8. Not engineers, we don't say 10. That'll get you the wrong answer. But yeah, okay. Now I'm just gonna, you know what? I'm lazy. I'm just gonna copy this and just paste it along here again. Copy, paste. Okay. Damn. Okay, so the net force. So let's always in this question, useful to draw a force diagram. So let's get started with that. First, we got force due to gravity acting directly down, because that's just what gravity is. And then we have so that's going to have two components. That's going to have a force going down the plane, and then a perpendicular force kind of like that. Oh, shit. Just pretend that's 90 degrees, okay? Oh, wait, no, it's not really. Okay. 90 degrees, I think that, okay, that's 90 degrees, okay? Now, we also have a normal force, normal, and I think that one's theta, yeah? Yes, we do have frictional force. Just bear with me for a moment. I think we proved that this, I think that was theta. I think due to like similar triangles, we can check that. Yeah. Okay. Cool. So remember in your labs that you proved that that angle was equal to that angle. Did I remember that? Yeah. Does anyone want me to go over it again? Why? Like. Yeah. Okay. Cool. Okay. Let me just make a nicer diagram. A bigger diagram. Okay. So we know that this is force due to gravity. This is going to have two components. Since it's moving along, this direction, and this, like, that's going to be our axis, because it's going to move in that direction, and then, it's just going to stay still in that direction. But, so we're going to have force going down there. That's going to be like one of them. And then this one's going to be up here. Now, obviously they should join, but I just didn't think of the magnitudes. So if you guys really want me to do that, I can do that. And that one's there. Okay, cool. And that one's like there. Now, everyone does it a bit differently, but I'm gonna do it the way I like to do it. Okay, now that's that. Okay. And then we got a 90-degree angle here. Okay, so that angle here, that's 90 degrees, because this is like a flat line. So this whole thing's 180, and that we know was 90 degrees because that's kind of what we needed to have there. Correct? Anyone objecting so far? No? Okay, because I made this angle 90 degrees. I'm just shifting it down a bit, so that angle's also like this is this and this is parallel. Is that making sense? Like, yeah. Okay, cool. Oh, that's just to make this a right angle triangle. So that's like this is perpendicular to this. Okay. So this angle in here. Welcome. This angle in here, which is, I'm just going to get a different color. That angle there is 90 minus theta, right? Because of our angles in a triangle. Yeah. So then this angle in here, I'm just going to different color actually. Where am I? Okay, no, that's not a good color. Okay, that angle there is going to be 90 minus theta, which is just theta. This angle here. Is that making sense? And then these are parallel lines because they're both going directly that way. And remember alternate angles in parallel lines? Yeah. So that angle's 90 degrees, alternate angles are parallel lines. This angle must be theta. Wait, let me just, yeah. And then that one's there. Is that making sense? Yeah? Okay, cool. Okay, let's keep going. Now, net force. Okay, hang on, let's just finish this force diagram. So we got a normal force, and then we got frictional force. Now, what have I got here? Okay, now obviously, the net force in the y direction is 0. Yeah, I'm just going to change that to black. The net force in the y direction is 0. Then I'll know why. Yeah, exactly. Not going up and down. So like, it's just sliding down. We can just say pretty safely, this is not moving like that. If it was, then our problem would be 10 times worse, and I would be pretty upset. Okay, so then that leaves the force net general equals the force net in the x direction. And that's going to be equal to, I'm going to say the force going down minus the frictional force. Now, if I've said that the force going down is, positive, frictional force is going negative, so my positive direction is that. So that's my, that is my positive direction. Is that all good? I've just defined it like that. Normally we say, right is the positive direction, left is not. Unless if they tell you otherwise. Now, the force going down is what? So, we got this triangle here. Oh, no. We got this triangle here. What do you think is, if this FG, if FG is equal to mg, what's the force going down the incline? Yeah? Yeah, because it's opposite, right? Because we have like an opposite there. So, pretty safe to say that force going down is going to be mg sine theta. Cool. Now, that's good. Now, the force frictional, just considering the magnitude, not the direction. Does anyone remember the force, like the frictional force? Well, kinetic frictional. Anyone remember what that equation is? Rn. Yeah. Oh yeah, un. Yeah. Yeah. The normal force. Yeah. It got to do with the normal force. Yeah, exactly. So normally it's it's okay. It's okay. We're all scared. Okay. Frictional force is un. Everyone good with that? Now, what's n? People may ask. Oh, okay, yeah. See, I'm not an engineer, so I was like, what? Okay, so normal force, we know from before that since there's no movement in the y direction, we can say the normal force is going to be equal to mg cos theta, right? Because, it's not moving up or down, so, normal force is going to be equal to the gravity in that direction, correct? Cool. Now, that's going to be UK mg cos theta. Plugging that in, F net is equal to mg. I'm just going to factor, actually, no, I won't. Minus mu k mg cos theta. Is that all good? Oh, because, yeah, so that's like implied sign. Because we know that the direction, like the force in the y direction, is 0. It's not flying off the plane. Yeah, exactly. Because like it's kind of like how you call it? If I place my book on this table, the normal force is going to be equal to gravitation. It's kind of like that. It's not, if it wasn't, my book would be flying up there or flying down there. So that wouldn't make sense in our scenario. Does that make sense?
It's cancelling that gravitational force in the y direction. Is what it's doing. So it stops it from falling through the plane. That's all it does.
Is that going to make sense? It's kind of like, okay, if I write it like this, mg cos. Would that make a bit more sense?
Oh,
Yeah, because it's just cancelling out. So. Cool. So from there, we can kind of just plug our stuff in. I'm just going to factor this out. So mg sine theta minus mu k cos theta. Plugging our stuff in, we had m is 2.02, theta is 25.6, mu k is 0.339. Plugging our stuff in, we can get, I'll just write it out, 9.8 sine of 25.6, oh no, 25.6 minus 0.339 of cos of 25.6. Cool. That's our FNet. Plugging that onto the calculator, if someone really wants to confirm, or just trust me, force is going to be equal to 2.50 newton. Oh, 5150. Okay. It says 51 there. When I put it in, rounding it, I got 50. Honestly, in the test, if you get done for like two decimal places being wrong, like 50 to 51, I'd be like, Tom, what the hell? I'd be like, Tom, what the hell, man? Like,
It's like, a bit of leeway in the exams. Like they give you like a little bit of like plus or minus, so that way if rounding error occurs, you can still get it right. But if you got it wrong, like in this, if you got it wrong, just email Tom and he'll.
Yeah. Like, also a tip, when you're doing questions, don't round until the end at all. If you really want to save stuff in the calculator, save it, but never round, just to get the more exact. Because if you keep rounding, you might get off by more than one decimal point. Is that making sense? Cool. Okay, so that's the second part. How are we going for time? Okay, I'll try to get done as much as I can. How good is this? Okay. Okay, now, part 3. I said A, B. Okay, you know what? C will make sense. Part C. Let's. Yeah. Sorry, that means down, and that means, I don't know, perpendicular. There we go. Cool. Okay. Now part 3. Suppose the block is now replaced by a ball made of the same materials. The coefficients of friction change. That's for us. With the same mass and given radius, r is 7.98 centimeters. The ball rolls down the inclined plane described in part 2. What is the speed at the bottom of the inclined plane? Okay. Now, first thing to ever do is, write your new value. Now, this is in centimeters. Always convert to SI units. Just do it. Oh, welcome. Take a seat. Is there more chairs? Yeah, there's more. There's one more over there. Okay, is there 2 more?
Too many grabs.
Oh, yeah. I think. Oh, yeah, just grab these 2. Can you just shut them over there? Yeah. Okay. Yeah, as I was saying, always convert to SI units. Just make it a habit. Make it a religion. So 798 meters. Because then people will be like, oh, why am I off by like 1,000? Like, what the hell? Like, it's because of that. Okay, so then we have, so that's, okay, that's good. Now, when we have a ball rolling down a plane, so I'm just going to, if I just like, what if I do that? Okay, cool. I'm going to write a new diagram. Okay. So I'm just going to draw a little diagram of the same scenario. If now I have a ball going down the plane, what's going to happen in this scenario? The ball's rolling, so it's going like, it's rolling down. Is the friction going to act the same? Or friction's going to change? If there's a ball like rolling down, if I like slide a book across the table and slide a ball across, like roll a ball across the table, which one do you think is going to go further? The ball or the book? Yeah, exactly. Because kinetic friction is actually not acting on the ball. It's acting, only static friction is, because you can think about it as like little tangents Okay, like only 1 point's hitting the table at a time. Ideal ball. Kind of like a tangent, tangent only hits at 1 point. Is that making sense? Cool. So we can say that's kind of how I like to think about it. So since it's a ball, I can say no kinetic friction. Cool. I'm just gonna make this a bit smaller. Is anyone still copying that down? Oh damn. Is anyone still writing that part down? Okay. Cool. That's just gonna go like in the corner there. Well, since it's a ball, no kinetic friction, good. And that's just because, the thing there, the surface just applies a torque to that. Don't worry about that. Just know that there's no kinetic friction acting. We're gonna think this problem in terms of energy because we want to find that the what the final velocity is. Where is it? We want to find the speed of the ball at the bottom of the inclined plane. We really want to find like VF. That's what we want to find. Now, we know that energy-wise, the change in kinetic energy. Well, what do we got? So we got kinetic energy. Well, hang on, mate. Translational kinetic energy plus rotational kinetic energy is going to be equal to the change in potential. Cool. Or I can just say change in kinetic is going to be the same as, change in, well, I'm just going to call it, it's actually negative change in U. Is that making sense? It's just conservation of energy, right? At the top, it has no kinetic energy because it's not moving. At the bottom, it has, all the kinetic energy, but it has no height. So potential 0.
Translational.
Oh, translational. Sorry, translational. Because, one sec, translational. Because now the ball, it's moving that way. It's moving that way, but it's also going to rotate. There's 2 ways it has energy. One, by just simply moving, and the other one by rotating. So, who can see what's coming next? Starts with I. Moment of inertia. So, good stuff. So we know that. So what's the kinetic energy formula for translational, at least? Anyone know what kinetic energy is equal to? Yeah, half mv squared. So I'm going to use this. I'm going to go half mv squared. Who knows the rotational kinetic energy? Anyone? It's very similar to this, but it's just like in a rotational. Was it? Close. Kind of. It's just half I omega squared. I is the moment of inertia. Cool. I is moment of inertia, and that thing is angular velocity. It's basically just the rotational version of kinetic energy, right? Your eyes, literally just think of moment of inertia as just rotational mass, and you're sweet. Except kind of, yeah. Just think of it as like if you're in a rotational form, instead of m, use I. We're all good for that so far, and that's going to be equal to. What's the kinetic? What's the change in Okay, also, so that's you can say that's final, and then I'm just gonna okay, cool. Okay, I'm just gonna write this down here, just to keep those labels. So the change in kinetic energy is going to be that minus K initial. Ki initial 0, right? Because it's not moving at all. Starting from rest. So does anyone mind I just kind of like rub that out? That's all good? Okay, cool. That's going to be equal to negative change in potential. Now, that's going to be equal to negative U final minus U initial. Obviously, that one is going to be 0 because we're at the ground, so that's cool. So I can just say, half mvf squared plus half I omega f squared is equal to ui, which is equal to mgh. That's the potential energy in a gravitational field. Does anyone object? Questions? No? Cool. I'm not scaring anyone. Now, what else we got? Now, we're gonna. Does anyone want to do a side quest to find the moment of inertia? Or do they know what the moment of inertia of the sphere is?
That's from like the 503.
Was it?
503.
Close. Close. It does have a 5 in there. So we know I have a sphere is equal to, what was it 2 over 5? Yeah. Yeah, 2 over 5 ml squared. Yeah. Does anyone want me to derive that? No? Yes? Kind of, yeah. It took me how many, took me like a page and a half in this tiny book. So, does anyone want me to go over the moment of inertia derivation of a sphere? No? No? It might take a while. But, look it up. Just Google it.
That one is your bullshit, isn't it? Yeah.
Oh, you guys are sweet there. Okay. Now, if I just add another page. Add page. Cool. Okay. Now, know that. Okay. How do I express the angular velocity in terms of the translational velocity? Like, if I ask you, like, omega in terms of V and R, anyone know the formula for that? No, not quite. Welcome, come in. Do you want to get more chairs? Do you want to get more chairs quickly? There's like one more up here. Oh yeah, kind of. Yeah. I can go on a side quest. Okay, so does anyone remember this from high school math? Just like the arc length in terms of the radius and the theta in degrees or radians, sorry. And remember that? No? You guys are scaring me just by this near silence. Okay. Well, I'm just gonna state it right here. It's that. The reason why is because if we have like yeah. Yeah, just give me one sec. Where is it? Okay. Okay, is anyone like scared of that omega? Okay, at least you're honest. It's fine. Okay, kind of? Okay, good. We love some honesty. Now, if I have a circle, oh no, that's a bad circle. Yeah, kind of, yeah. Because if I have like that, and then I think, does anyone remember that this length? That's how we define radians, right? That's how we define radians. L equals R theta. Theta's in radians. Shit.
I did not mean to do
that. Okay. Okay. Hopefully YouTube can, or the transcriber cannot transcribe that word. That would not be good. Okay. So we know that, right? From just math. Now if I do DL, dl dt. It's just going to be that, right? If I just derive both sides by time, I just get that. The radius is not changing. It's just a circle. So, I can go dl dt. That's just what? A distance over time, like velocity. Is that all good? So I can kind of come over here and say v is equal to r. Now, changing theta with respect to time, what does that sound like? Kind of sounds like I'm changing. What's that?
I'm not going to say it.
Okay, no. Maybe some chocolate will help. Get your brains working. Anyone want Mars bars? I have some Mars bars.
Is dl over dt equal to v because distance?
Yeah, that's L. So that's L we have there. That's V. Translating over. If I'm changing theta, hang on, I'm just going to check this out.
Eat chocolate.
Eat chocolate bars. Oh my god, no more caramel koalas. Wow, that's everyone's favorite.
Yeah.
I'm the only one who's like not a fan of caramel koalas. I prefer Mars bars, but sad I can't eat chocolate. Now, okay, let's think. If we have a changing angle with respect to time, kind of sounds like angular velocity, right? There we go. So, if we have that, rearrange, we get that. Is that making sense? Cool. Let's move on. What's that? Because that's so the L is an arc length, right? If I'm in length, like, and go over in time, like, if I transverse an L in a certain time, that's velocity,
Are
right?
you not integrated, or am I thinking the wrong direction? Because like, you integrate from acceleration to velocity or velocity?
Because like to go from displacement to velocity, you derive it because it's changing position over time. Cool. Okay, now, so then our equation becomes a half mv squared. That's our translational. Half 2/5 mr squared, and then this becomes v over r squared equals 2. Now, the height is a problem. But that's okay. That's going to be our height, right? And the length of the ramp is that. So how do I express h in terms of L? Because we don't know h, but we know L. Trig? Anyone know trig? Yeah. So that's an opposite. That's the opposite, and that's a hypotenuse. What does... Yeah, so sine theta is going to be equal to what? H on L? Then h is going to be equal to L sine theta. Is that making sense? Yes? Okay, cool. We're getting a few nods. I'm happy. Okay, so then MGH. So that was, our formula was... Is this too messy for you guys? Should I try? Can you guys read that? I'm getting a few nods. Can everyone read it? Is everyone like, okay, cool. I'll be neater. Okay. MG, because that's what we had starting. And an H becomes L sine theta. Is that making sense? Yes? Okay, cool. I'm getting a
MR squared or
MR squared, because that's because we found that, so we know that this is our formula that we need to use. So this is the formula that we need to use here. Oh damn. Okay. And then I'm gonna get rid of that. That orange box is what we want to use, right? We were mentioning that before because we had the kinetic rotational and kinetic translational. And then we just said that the moment of inertia of a sphere is 2/5 mr squared. I think Liz derived it in your lectures. I'm not going to drive it again merely because of time. But is that making sense? Yes? Okay, we're good. And then the V over R is because of that angular velocity. I just squared it because it was squared. All good? Yeah? Okay, cool. Okay, now subbing our values in, Also, I can just simplify this a bit so we can, not be as bad. mv squared equals to mgl sine theta. Now, I just, cancel the two r's because I did not want that there. Is that making sense? Yeah, I just cancelled like that one and that one because that's squared. Is that all good? Yeah, cool. What was that? What was that? Yeah. That's why I kind of cancelled it, so we don't have to do as much subbing in, because subbing in R would be completely useless. Cool. Now, I could also cancel these terms just to make my life easier. We can say half v squared is plus. I could also cancel the two 2's here. So that makes our life fun. Plus 1/5 v squared is equal to gl sine theta. All good? Yes. Cool. Now, yeah. Cool. Now, what are we gonna have? Okay. We sub everything. Oh, okay, we can also rearrange to this 10/7 gl sine theta. Is that making sense? Just adding the like terms of v squared and just do a bit of rearranging. Then anyone believe me? Anyone not believe me? Kind of do it yourself. If you guys want me to, you guys really want me to go over it, or all good? Believe me? Yes, trust me. Source, trust me, bro. Okay. Now v is equal to the square root of that. All good. And then we're not considering negative because negative velocity. It's also going down the ramp, so I think would be good. So subbing all that in is going to be roughly 3.13 meters per second. Don't forget units. I think it already gives you units there, so you're sweet. And again, 3 significant figures because that's what everything else is. Is that making sense? Yes. Oh. Yeah. Oh yeah. No. L value. Okay. Yeah. L was 1.62. Sorry. Well, what's the? Oh, yeah, that sounds about right. Yeah. I mean, when you think about it, like the ramp is kind of like in real life scenario. Ramp's gonna be like from here down to like what there to like there, more or less. And you got a
11
ball.
kilometers an hour is like 2 times the walking.
Yeah. Also, like, have you ever rolled a ball down a ramp that far? Kind of gets like picks up velocity pretty quickly. Yeah.
For when you got H equals mg L sine theta, where did the mg come from? And
Wait, H equals to what?
like what's the mg?
Oh, the mg came from. Sorry. Yeah. Okay. The mg came from that because that's our potential energy. Yeah. So you got mg and then the H is L sine theta. So we just said L sine theta. Yeah. Oh, good.
How did you like to equate the transitional energy and the rotation?
Good question.
In my logic, they would just see that just use the kinetic. That's it.
Yeah, that's a good question. Okay, so he's asking why equate the
What
energy?
you told is
Like why equate the energies?
yeah.
Okay, good question. Because I mean we want to consider what all the energy is in this. Right? So if we count them, we obviously got one going down the ramp, so that's going to be our translational. It's a ball, so it's rolling, so it's going to have some rotational kinetic energy. But then that also there's a potential energy because it's up the ramp. So what we know that the change in kinetic energy. Where's my equation? The change in kinetic energy is going to be equal to negative change in. Right? They're just going to convert. Now that's true for like ideal systems. Obviously, if there's like external forces, friction playing a lot, not necessary. Is that all good? because it will lose energy in heat if it's friction.
So you just gotta remember when reading these questions, there are actually like keywords in these questions that are put in there specifically to make you think like that. So I think what you're asking is how do you think like that?
Yeah.
I don't.
So you need to read every single question, every single word in this question, because every single word actually does have a meaning. They're not just like questions that you to plug in numbers. Okay, we're not in high school anymore. We're in university now. So we're actually trying to do things properly, and we're gonna try and get things. So it says it's replaced with a ball. Okay, so we know that it's a ball now. It's no longer a square. So what does that mean? Well, it means that it rolls down the inclined plane. So we know that it's rotating. So when something rolls like this, okay, we know that it must have rotational energy. Okay, and rolls down the inclined plane described in part 2. What is the speed? So you know that what is the speed? You're going to have something to do with velocity. Rotational, okay, so I can get energy out of that. Okay, so I have kinetic energy. I know that because it's moving down, I know that it also has translational kinetic energy. So therefore, I need to add them up together to get the total kinetic energy. Because kinetic energy is one of the very good things that follows the law of superposition. Everyone knows what superposition is. If you have something, then its total is the sum of all its parts. So, for example, if Davide and I are pushing a box, okay, the total force applied on that box is the force I'm applying on it plus the force Davide is applying on that box. Right? Does that make sense? So to add up kinetic energies, well, I just add up the rotational and translational. And I know that the change in kinetic energy is equal to negative the potential energy. So I just write that. I write that all down. I remember Tom sent my 1A class last term videos about like how to think like that, and a lot of the energy stuff is literally just like, okay, what energy can be applied to the system, and then you just add them all up. And when you do it on both sides, everything all works out. So that's kind of, you really do need to read the questions, and you will get better at it the more questions you do. It's literally just a matter of doing questions and learning. It's about as yeah. So I hope that makes sense. But
Yeah. Also, just had to add on to that, like, really, the only other way I could probably think about going up this question is using your kinematics formulas. Well, it's like S equals to like half whatever, like one of them. Because you have your acceleration and there's initial and final velocities. But then, that's just. But then, actually, no, you can't consider because I think that's just assuming an object rolling down, like just an object just kind of moving.
it doesn't consider rotational.
Yeah, exactly. So if you have a ball, you have to consider rotation. So always, that's we're big enough we can do that.
Yeah, so that's why I'm saying there are keywords in every question. So as soon as you see rolls, you need to think, okay, so it's rotating, there's rotational kinetic energy. And the only way you can think like that is if you know the content. So these questions, although some of them actually like piss easy, like some of them literally like look at the formula sheet and tell me what the formula says. But some of them like this, they do require you to think a little bit. And you've got to do a bit of critical thinking to be able to answer them. Yeah. So you need to know your content to be, if you really want to do well in this course, you need to know your content pretty well.
Just to, I don't know if anyone was confused as why I was talking about friction at the start, is because the friction is just merely why the ball rolls. Because at every infinitesimally small point on the sphere, there's going to be a torque because of the surface. It's applied torque. Instead of just sliding down, there's friction, so it rolls. Is that making sense? Yeah?
Since we know there's kinetic energy in this question, right? And like we can relate that to the concept of energy where it converts to potential, then that's how you.
Yeah, so we know that energy is conserved in this system. So we can always say, we always know that delta K is equal to negative delta U. We know that for everything where energy is conserved.
Yeah.
And we know that the total kinetic energy in this system is translational and rotational kinetic energy. So we can equate this. And when you do negative delta U, we know that the initial, I think if you scroll down, David, if you don't mind. So we've actually just expanded it here, okay? So we know that the rotational and translational kinetic energy added together is the total kinetic energy because of superposition. We know that, okay? And negative delta U is minus U final minus U initial. We know that U final is 0 because MGH, when it's at the bottom, H will be 0, so that'll cancels out. The negative cancel out, so we get U initial, right? So it's a lot of it is literally just expanding formulas and cancelling anything out. A lot of this is literally just cancelling stuff out before we even answer the question. And then when we get our final equation, if you can scroll down a little bit more, we get our final equation, right? We can see that it's a little bit scary, okay? But all you need to do is just start cancelling out terms, and you get a simple equation like half v squared plus 1 on 5 v squared, okay? That's easy. You know, you just factor all that out, and then you get v squared times half plus 1 on 5. We all can add fractions, right? And then we move it over to the other side, and we get a very simple equation. We just plug and chug numbers, and then we get an answer. So a lot of it is putting in terms, getting an equation, and then cancelling everything out, and it'll work out in the end.
Cool. And yeah, I mean, look, you could sub in all the stuff with that equation. Here.
Oh, that one.
Yeah, I mean, you could, and then you could rearrange just to have v by itself and have all the stuff in there. But, not doing it. Yeah, you could do that, but then like, why put yourself through the struggle of subbing in everything when you don't need to? So that's why I simplified it a bit so I can make my life a bit easier. All good? We're all happy about that question? The uncertainties? Good. It's been an hour-ish, so just have like a 5-minute break. So I don't know, go get a drink, eat some chocolate, walk. Sure. We'll be back at 10 past. What? Because I've got solutions.
Yeah.
Yeah. If you want, I'll show you which questions there are to go. So we have this question to go still.
Oh yeah, I remember this one.
Yeah, it's fresh in the head. Then we have this planet, and then we have a canonical pendulum, another plain question, and I want to do that one because someone mentioned maths.
Yeah, you can do that.
And this one I haven't done solutions to, so I'll be like freeborn with this one. And that's it.
Fair enough.
So if you want to do like,
I'll do a couple, if you don't mind.
yeah, if you want, yeah.
Yeah, I'll do some.
Sure.
I like physics. I can do physics.
Are you guys like a bit like a free for like a bit after this? Like 10 minutes?
Yeah. Because I start teaching at 2. I start lab doing it 2. So 1 I have like
Yeah, because I have a thing I want to ask for like PHYS1A.
fundamentals.
It's no physics and day situation. They just get you
Which one?
Physics and everyday like situations.
Oh yeah.
There's a question I have for an experiment, and I'm like really uncertain because of how much like it's trying to it's like you try to get the refractions index by not like using any lasers. It's like observation. I not.
Yeah.
I don't
Ask me.
just
Ask me after. Yeah.
Thank you.
That's alright. Oh, yes. How are you feeling so far? Really, right? We've got a lot of questions to do. Can we just make it through? Actually, I might try speaking. Because there's also good diversity. Just a preview. We got that question about like just kinematics and velocities and stuff. We also got like a planet stuff, like planet. Yeah. And then we got a conical pendulum. That's one of the hard questions. And then we got probably skip that one. If you guys want to try that, go ahead. Because there's already a solution there. And then I want to go through this one because linear densities. I might actually just do it because like I want to speed run because I like a shit ton of questions.
Yeah.
If that's all right. Yeah. And people can just watch it back and right. Yeah. If that's okay. Yeah. Okay. That's my minute for chocolate of the day. So. Is it week 7, right? Yeah, test. Yeah?
Yeah.
Nice. That's just like what, in your OTH time? Can't remember.
Same as me.
Huh?
Same as me.
Oh, you got 1B next week, yeah?
Yeah.
How are you feeling about the course in general? Do you guys like the course?
Yeah, it's fine, but
You don't have to say yes. I didn't like it. Either. I didn't like it.
I find it fine. It just, I don't feel like there's any time to go over anything.
The reason why, yeah.
Especially
Like-
asynchronous lectures, it's like 4 weeks.
No,
Oh,
asynchronous
trimester.
actually goes in because
Oh, that's-
I agree.
I really like
Asynchronous
it.
lectures.
they're like, hey, we teach you like this thing for like 10 minutes and then you're gonna do a question.
I love
Then we're gonna teach you the
I
next
love
5 minutes.
asynchronous lectures so much. The thing that I didn't do in 1A was go over the asynchronous lectures. I'm in 1B, right? I go through my lectures 1 week, and then that weekend I just go through the asynchronous lectures, and you have a much better understanding of it because you go over it again, and you do more questions on it, like in real time. The asynchronous lectures are so good.
If you don't have time to do both lectures, honestly, just like, because like with physics and maths, literally how you learn, like it's not like like law. We just watch a lecture and go, oh yeah, I understand that now. It's kind of like you actually have to do it. Like you can't just like oh yeah, circular motion, blah 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 blah. Like you can't just like absorb. You have to actually do stuff. So you have to do it with problems. That's like what you should spend most of your time on. Because that's when you think about it. That's what you do physics for, to solve problems.
I would say honestly, if you were to choose between the lectures and the asynchronous lectures, I'd say go with the asynchronous lectures every time because they force you to do problems. But if you can do both, because now I'm in 1B and I do both and it is so good.
That sounds much better. I do myself for this test because my lecture was not nice.
Yeah, I mean, yeah, it depends on who your lecturer is. Who's the lecturer in 1A? Tom? Is Tom lecturing in 1A? Like the live lectures.
There's the one stream A and stream B. Stream A was like some guy named like Raj or something like that.
Who?
I don't know, but I don't remember his name.
Fair enough.
Do you remember his name?
Rajiv?
Could be, yeah.
Yeah, Rajiv, yeah. He's alright, yeah. Yeah.
Wait, is he the?
I had him last term for experimental. But yeah, he was a
Oh, never
convicted.
mind. He's that computational guy.
Yeah,
that's right.
He's the
His research is
physicist.
very cool. Yeah, I think he's theoretical. I think.
He's a computational. I think it's what he's actually in love with.
So he studies like qubits, like quantum computers.
Yeah,
So
yeah.
his research is very cool. Okay. Let's get started. I'm gonna power through these because we have a few questions I want to mention. Now, okay, let's get started. The graph shows how acceleration of a cart along the x-axis changes with time. The cart starts with a speed v0 equals negative 3.75 at a distance of that. Cool. Just gonna underline these. In the graph, the acceleration is 3.72 meters per second squared. Time at A, which is that thing there, is 6.86 seconds. Time at B, which is here, is 13.72. And then what is the velocity of the cart along the x-axis at 3.43 seconds? Cool. Now, 3.43 is roughly what there, more or less? Straight line. More or less, right? We all on the same page? I think. Oh, I'm just going to draw that again. Okay, that's like what? 3.43. Now, this is an acceleration versus time graph. If I have dv dt is equal to a, rate of change of acceleration, how do I get what's v? Like, how do I express v? Yeah, the integral. Literally, the integral of a dt. Or, as we commoners call it, the area under the graph. And this graph is quite nice. So literally, we want to find this area here. Now, that's pretty good because we can just go 3.43 times by AA was 3.72 meters per second squared. So that goes 3.72. And punching that in your calculator, you get roughly this, right? Yeah, oh, not quite. You get this. 7596. But since V naught was negative 3.75, we're gonna do yeah, okay. So we know change in velocity is that, because that's just the area of the graph. It's just, the change in total from T1 to T2. So in reality, we go V final minus V initial, I just call it V naught, is equal to the area T1 to T2, or Ti, or T naught to T final of A dt. And we said that was 12.7596. So we know VF plus 3.75 is going to be equal to 12.7596. Is that all good? Yeah? Cool. So then we just rearrange the other side and we get a velocity of 9.01. Now, what do I want to say? Right? Does anyone have any questions? And that's, meters per second. Anyone questions so far? It's just the area under the graph. And you also have to consider that there was an initial velocity. So you have to consider change in velocity, because that's really what the integral is. It's a change in velocity. Is that all good? Yes? Okay, cool. Let's move on. That was part A. Part B. For an expression in terms of t for the velocity along the cart from between t equals 0 and t a, which is 6.86. I'll just zoom in. Evaluate the expression as much as possible. Okay. Now, what do we have? We know a is equal to dv dt, and then that's just we can just say change in v over t, or change in t. It's just the same thing. It's just notation, which is just equal to vf minus vi over tf minus ti. But we know ti is equal to 0. We know that tf is equal to ta, which is equal to 6.86. vi is equal to what? Minus 3.75. And then oh no, hang on. Sorry, not this. My bad. Where am I? T final, I'm just going to call t, the variable t, because we want to find an equation of, v in terms of t. So at a certain time, that means vf is equal to v. At a certain time t, I'm going to get a velocity v. That's why I keep those two as variables. Is that making sense? Yeah, cool. That's v. Okay, so I'm going to say v plus 3.75 over t. Is that making sense? Cool. Now, rearranging, I get v is equal to at minus 3.75. Is that making sense? Cool. And then our acceleration at that point was, where are we? Is 3.72 meters per second squared. So we plug that in because it's, the acceleration from this point to this point, which is what, 3.72 we said? Yeah, 3.72 minus 3.75. All good? And then I think the question already has your units here, but if not, we always know that it's moving in that direction, which is just the, oh no, sorry, not that direction, that's just time. we know that it's moving in the positive x-axis because it's has a positive acceleration, so it's gonna go in the positive direction. So we can say that's I meters second. Is that making sense? Normally gives you units, so you should be sweet. Yeah, just as an expression for v in terms of t. Cool. Now, what is the position of the cart at that time? Okay. Now we could, in this question approaching it, we could go two ways. A very, very long way or a very quick way. Let's do the quick way so you can save yourself time. The very long way would be like getting all your kinematics formulas, maneuvering around that to try get the position of the cart, like how far it's traveled basically. But to save ourselves time, what we're going to do, we're going to draw a position time graph, right? That's going to be, velocity time graph. That'd be much easier for ourselves. So at a velocity of, from t to, so we know that that was from t naught to ta, right? Was all making sense? Yeah? That's just 0, so I'm just going to replace, 0. So I'm just going to call this part TA. That's just V, that's T. At this point, it's going to have some sort of graph looking like that. Correct? That's just kind of what that looks like. And after this, we know that the acceleration is 0. So no change in velocity, which means our graph is going to be straight. Oh, our graph is going to be straight like that. Oh my, what's happening? Cool. And that is going to be, I'm going to call that T. They said B, right? Yeah. TB. Does that make any sense so far? So now, similar to before, if I have dx dt is equal to v, what's x? I don't know. Yeah, area under the graph, exactly. I can just say the integral of v dt, or just, area under graph. Cool. Now, what are we saying? Okay. Now, first we need to find this area, and we want to find this area, and we want to find this area. Split our problem into 3 parts, so it's much easier for ourselves. Now, how do I find this? That's just the x-intercept when y is 0, when v is 0. So it's going to be what? 3.75 over 3.72. Does anyone have a calculator? What is that equal to? .08. Okay, 1.008. Okay, cool. Cool. Okay, so then I'm gonna call this. Where is it? Area 1, Area 2, Area 3. Area 1 is going to be half times by base, which is 1.008 because it's time, times by the height, which is going to be 3.75. That's all good? Okay. Oh, it's actually negative 0. Because it's under the graph. So, what's that in the calculator? Does anyone want to punch that in? Very quickly. $1.89. Cool. 1.89. Yes, negative 1.8. Cool. If I can move this, that's a negative there. Cool. A2, similar to before, half times by the length, which is going to be, what's TA? TA was, 6.86. So you got 6.86 minus 1.008 times by the height, which is, what is the height? Yeah, well, the velocity at that time. So, velocity at TA, which is, we can just plug in TA. So now V at TA is going to be 3.72 TA minus 3.75. 3.72, 6.86. What it said there, right? Yeah. Minus 1.008. Does anyone want to plug that into calculator really quickly? I did not evaluate these problems. 21.77. Cool. So A2 is equal to half 6.86 minus 1.008. Wait, sorry. Oh shit. No, my bad. Can you reevaluate that? Is it that? 25.2. Cool. So then that will be 25.52. That's all good. And you don't want to punch that in a calculator quickly? $74.4. Oh, 74.7. Okay, cool. Cool. And then the third one is just TB minus TA times by 25.252, because that was just that value there. Oh, roughly there. Let's just try and get that a bit more good. Okay, cool. Now, which is, what's TB? TB was 13.72 times by 25.52. Last oh yeah, my bad. So I was thinking multiple before. Thanks. Can anyone sub that in calculator? Okay, we're good for time. Wait, 175. Yeah, cool. Okay. Now, adding A1 plus A2 plus A3, remembering A3 is negative. Sorry, A1's negative. We get what? That looks like 100 and... What was that? Yeah. Okay, and now, not quite there yet, because... Yeah, like we do, so it's,
So everyone's already a negative number, so we can just...
Yeah, no, so like, what's, did you put the negative sign in front of this one? That's all right, so it's what, gonna be like 70, so it's gonna be like 72-ish? $247? Oh, hang on. Oh, okay. So what was the value? No. That's all right. That's all right. Now, what are we missing? Anything missing? Okay, well, I did it the long way, and I got the right answer. I did it the short way, and then I get the wrong answer. Damn, it's embarrassing. Shit. I mean, because then if we just minus... Because even if we consider the initial x at negative 5.1 meters, we still get something very big. Okay. Strange. They don't know where it went wrong. Okay. Does anyone know where it went wrong or not? Which one? Mm-hmm.
So he has to minus the initial velocity.
Because that's the answer there, so that's good.
So that.
Ah, yes.
Oh, yeah, you're right.
Yeah. Damn. Okay. Okay, that's okay. That's just gonna affect our area a little bit. We're just gonna make it lower. Screw it. Calculator time. Let me get my calculator out. Okay. Yes, I'm using my phone as a calculator. 1, 2. Damn. 2 times 6.86 minus 0.08. No, my bad. Whoops. For this, the new value of phi. Yeah. 21.8. Cool. Yeah, that sounds right. Yeah. That should reduce it that much. Okay. Half times by 6.86 minus 1.008. But this second, this is going to be 63.7868. And then that's still going to reduce what? It was like
A3 is what you're going to reach.
A3, why?
Because the velocity's changed.
Oh, yeah.
There you go, that should fix it.
That might fix it, yeah. Damn. 21.8. That's what? I've got a scientific calculator on my phone, so it's actually it's a good calculator. Trust me. Yes, okay. Wow. Really? No, it's not. It is so bad.
So worthless.
No, the best calculator is Maple.
No, it's not. As if it is not. Are you? Nah.
Maple is so.
Nah. Maple.
Are you guys all in when you guys for your second lab test, it's all on Maple. Yeah. That's when you'll learn to love Maple.
Yeah. You realize, wow, I don't understand any of this garbage anymore.
I hated Maple up until lab test 2 when you needed it.
1B, the second lab test is the same thing.
Yeah.
It was Maple
Maple's for most of it. So trust me, and when you get to your final exam, you will just be using Maple. I promise you, Maple is so good. You just gotta learn
You
it.
don't have to think about anything. Just like,
Exactly.
Just like, I did this.
How good? Exactly. How good?
It's so awesome. And then people like start in GPT like, oh yeah, that's stupid.
No, use Maple.
Yeah, there we go.
And so,
I tried to download Maple on my phone, but it wouldn't recognize my uni account, so it doesn't work. Asking me to pay like $200 a year to use it. I'm like, no way.
okay, finally we got there. Okay, cool. Meters. Cool. Thank you for spotting that. Okay, a little 5-minute detour. That's okay. By the way, I have not used Maple since first year, so I honestly don't know why I did. I'm maths and physics. So I'm a third year, and I can't even. I still have I don't get like the instruction manual for Maple. Yeah, I still have that just stuck tucked away in my.
Why don't you use it? What do you use something else?
It's Python. I always use Python or like MATLAB.
Oh, okay.
Yeah, MATLAB you use a lot. Python or MATLAB.
Python's good actually.
Python probably not for integral.
No.
Integral, I use integral calculator online.
You can
The Symbio lab?
I think so. It's like
Symbolab,
it's
yeah.
like a no, not Symbolab. It's like a beige background. It's literally the website.
Integral calculator, just like it's.
Yeah, it's literally called integral calculator.
And there's also derivation calculator.
Exactly.
Same thing with
Oh yeah.
It's so good.
It's made by like this one Polish guy, and then he's like, oh yeah, I just gonna make it
Oh, the cross product calculator.
Is there a cross product calculator?
Yeah, and then
This
the
is
dot product
everything
calculator.
calculator.
Wow.
Yeah,
You can do cross and dot.
if you're making dollar units, how we don't have to do this crap anymore.
So one time I contribute to this
Like,
class.
and then like the team is like, oh, use 10 calculus, we need you to know it, and then they're like, and then they're going like just typing on Maple like,
Okay,
Okay. Let's do the next. Everyone, sorry, is everyone all good with that? Sorry, that was just. Everyone make sense of that?
Yes.
Cool. Yeah. If you want to take a photo, I'll leave it there. Like
So just don't miss that minus. The minus of the.
that really messed up everything. Wow.
Yeah.
It kind of like made a domino effect. So yeah. Is that making sense?
Yes.
Cool. Okay. Now, is anyone still want to take a photo of that? Yeah. Okay. Cool. Yeah. Your hand camera. Okay.
The comedians is the one.
Oh yeah.
The average Victorian child did not come.
No. Okay, now next one. Okay, this planet has a radius 8,228 kilometers with a mass, like a huge mass, of 9.69 times 10 to the 24 kilograms. I'll make that a bit there. Small holes drilled through the planet, which is there. I'll just draw that. Consider an object with mass that the object can fit through this hole. And I just assume it's like a long, thin rod that weighs 474 kilograms. Don't ask me how. Maybe it's a really long rod. Yeah, I know. Probably. Someone I hate this question. Oh.
Is this the question where you put like gravity?
The force due to gravity is like over r squared. So the smaller the r, bigger the force.
Yeah.
So yeah. Now let's write our numbers down because they're all in weird units. Okay. So RP, I'm gonna write as 8,228 times 10 to the 3 meters. Because we just want it in meters, not kilometers. Because SI units we love. We don't really like anything else. Mass of the planet was given to us in SI units. So that's nice. 24 kilograms. This 474 kilogram object, I don't know what it is, but it's 474 kilograms. Just allow it. Now, let's speed run this. What's the object? Well, when the object is a distance 123 kilometers away from the planet. What is the magnitude of the gravitational force the planet exerts on the object? Cool. Now, I can write G is equal to 123 times 10 to the 3 meters because we want that. Now, Newton's gravitational formula was what? G, what was it? Yeah, MP M naught on r squared. Now, r is interesting because we got to consider this, right? It's a like the object is there, so it's a distance, rp away, but it's also going to add the distance d away from the planet, the surface of the planet. So we're going to say r is equal to rp plus d. So the force is equal to g mp m naught over what was it, rp plus d squared. Right? Yeah, right. Now, if you have g is equal to what, 6.67 times 10 to the negative 11, that's it. Yeah, good enough. Unit meters squared per kilogram squared. Now, plugging all that stuff in, I'm just gonna get it done. It's just equal to roughly just 3 significant figures. Newtons, 3 sig fig. So we have 4,390 newtons. That's the magnitude of the force. Is that making sense? Yeah? Okay, cool. Let's move on. Now, what would the magnitude of the force be due to gravity of the object when the object is on the surface? So object on the surface. That just means that we're not considering d anymore. So it's literally the same equation, but d does not matter anymore. So that doesn't matter anymore, right? Or I can just say this. Go. If I want to do that, square it. All good so far? Cool. Plugging that in just gets you straight to roughly 4,530 newtons to 3 sig figs. Cool. Any questions? No? All good, all good, all good. Okay. Actually, Lachlan, do me a favor. While I'm doing the question, can you just like pass this around?
Oh, yeah.
Yeah,
Yeah.
cheers.
Alright. Need everyone to scan this QR code because we get money. If you haven't scanned it, if you bought, yeah, I know a lot of you can.
Oh, yeah.
So,
Yeah, whoever hasn't scanned it, scan
yeah,
it, please.
Money.
What do you guys do with the money? Like, is it beer money?
Well, we buy the chocolate.
No, ARC doesn't fund alcohol, so.
No, it doesn't fund alcohol, but like they pay for like food that we get on a pub, for example.
Yeah, that as well. Also, like
All the chocolates.
chocolate, as well as if we get money, we can host even better events, like the pizza party. That we get funding for that. Also, for last time we had a pizza party.
It should have asked you like if that idea.
Was that?
Yeah.
What year saying? What year are you? First year?
Yeah.
Yeah, just skip one. Yeah. Right, this meme. Yes, that was Lachlan. Yeah, that was Lachlan's meme. Okay.
Explain to me.
An object. Okay. Again, object falls through the center of the planet. When it is at a radius, when it is at that radius, what's the magnitude of the gravitational force exerted on the object? Okay, cool. So now we know R naught is equal to what? 3,291 times 10 to the 3 meters. We literally use the exact same formula again and again and again. Yeah, literally, like everyone gets scared of planet questions, but this one's a pretty good planet question.
What's the one that's like negative, always negative until you reach the gravitational potential?
Yeah, probably that. Yeah, that's potential. And that's it. Yeah, that's like something different. Maybe no R squared on the bottom, but it's just R. But cool. So we get that now. Now, here's a catch. Here's a catch. There's a catch to this question. It ain't that easy for you guys. Now, calling that M. Why? Because if we consider the object, I'm going to draw it, redraw it. Okay, let's just draw this. Okay, that makes sense. And that's at a radius R0. That's at a radius RP. Now, note that since we're actually at the so you know how I said that more force is going to be acting on the object closer? Was it? Yeah, because less radius, more force. That's a lie. Because we have to consider that since we're in the planet, less of the planet's mass is going to be acting on us. Correct? Because we can use a little something called Newton's shell theorem. Has anyone heard of that? Newton's shell theorem? Basically, okay, all that is that if there's an object sitting here, none of this stuff, none of this stuff around it is going to be like acting on that. Or we can, just say that, just because, yeah. So basically, we ignore, the mass doesn't act on that. We just, it's acting on this mass in here only. The reason why is because I think it's just got to do with, it's, acting, this part is acting on this, the same as that. So it's all going to cancel. Is that making sense? Cool. Sounds legit. Cool. So Newton's shell theorem says that we can't consider the whole mass of the planet in this question. So it is a bit different. It's not as easy. So we know that the mass is equal to the density times by the volume. So we know that. So then we can say this is just equal to mass of the planet over the volume, which is 4/3 pi rp squared, r cubed, sorry. And then we know V of this, I'm going to call this V0. V of this small section is going to be 4/3 pi R0 squared. Making sense? Cool. Okay. Now, plugging all this in, we get MP over 4/3 pi RP cubed times by 4/3 pi R0. Oh, cubes. There we go. R0 cubed. Oh. Is that making sense? What was that? Oh, this is the mass density. Because you know that rho is just equal to mass per unit volume. Because that's like the mass density of an object. Like, it's like the amount of mass per unit volume, right? Yeah, we do. Haven't you guys used mass density before? What do you guys have?
It's just like by definition, like for example, like lambda's linear mass density, so M over L, and then sigma is
surface density. And then rho is.
That's just something that you guys will have to know.
I mean, you guys have used it in certain experiments, including having what experiments in 1A do that?
I don't remember now.
I don't know if there's an experiment, but you guys do get taught
There's
mass.
a linear density one.
Yeah, so you guys do get taught volume density in first year physics, and it's basically just saying that it's just mass per unit volume. So like, I don't know, for example, what's like some metals, or like a lot of metals have different mass per unit, like mass densities. Like tungsten, for example, has a very high one compared to, I don't know, like copper or whatever. But is that making sense? Is everyone all good with that mass change? Yeah, cool. Because we're only considering this mass in here, not considering the outside. Okay. Now I can cancel a few things. That's just lowercase p, or like subscript. So calculating that, I can get MP R0 and RP cubed. Is that making sense? Yes. Okay, what time is it? Okay, I've got a bit to go. I'm gonna do that question. Okay. Now, so then we got force is equal to G M naught on R naught squared. And that's just equal to G, and we, sub this in. G, we have MP R naught on RP cubed multiplied by M naught on R naught squared. Yes. Is that making sense? Yes. And then we can also just say that's just equal to G MP M naught R naught on RP cubed. So we get our final answer as roughly 1,810 newtons for 3 significant values. Is that all good, guys? Not confusing you too much? Any questions? All good? You guys can ask me after, because I have an hour after. So, cool. Okay, moving on. What are we going to do first? Someone did mention center mass, but there's also a cool pendulum question. What are we thinking? Do we want to do this question, the linear density question? Or we got a conical pendulum, which includes circular motion.
Hands up for linear density.
Circular motion, conical pendulum. Got it. Hang on, wait. Okay.
Alright, hands up if you want to do a linear density question. 1, 2, 3, 4, 5, 6, 7. Hands up if you do the circular motion question. 1, 2, 3, 4. Sorry, guys.
Which one? Which one?
Linear density.
Cool. Okay, linear density. Now, what I'll do, I will do this problem, and then whoever wants to hear the conical pendulum question, I can do it up on the board after. So then, best of both worlds. Okay. Now, this question was where? I think that one. Okay. Linear density of the rod is described by this. Right? All good? This is what our rod looks like. Write an expression for dm in terms of dx. And x, and yeah. In terms of x and dx. dm in terms of x and cool. Now, not to note, I remember one person put on Discord about why am I getting this question wrong? I think it was because they put dx as d and x together, two separate variables. I don't know what the syntax is to put dx.
No, I think the reason that they got it wrong in the Discord was because there was a dx already included on the question, not for this one.
Okay.
But in these questions for Moodle, when you put dx, just put it as dx, and then but you still need to put a multiplication symbol like an asterisk when you write it in, if that makes sense.
D asterisk X.
No, okay.
Yeah, just write it down.
It'll just be a. So for this answer, right? If I was to write this answer in Maple syntax, I'd probably go. It doesn't really matter which way you do it, but 4.27x. Or actually, sorry, I should probably. Two seven asterisk x plus 2.16 asterisk dx.
Cool.
It doesn't matter which way.
Okay.
Dx,
Yeah.
obviously, but so you'd have to put the asterisk for the multiplication, but you wouldn't put an asterisk between the d and x. And that's our Moodle syntax.
Cool. Okay, cool. Oh, Moodle? Oh, shit.
Moodle, not Maple.
Yeah, my bad. Every time I say that word, it's gonna transcribe. So hopefully it finds another word. Okay. Now we know that lambda, linear mass density, is gonna be the mass of the rod over the length. Or I can say some small incremental mass at a small incremental distance. It's just the same. Now I can rearrange that like this and this. So I can say dm is equal to lambda dx, And we know lambda was 4. Oh, yeah, my bad. Dx. Lambda was 4.27x plus 2.16. So dm is equal to 4.27 x plus 2.16. Yeah, maybe get rid of that bracket. Okay, and that's going to be dx. All good so far? Pretty standard question. Okay. B, what is the total mass of the rod? Well, what do we think? What do you think, guys? How are we going to approach this problem? Total mass. From dm, how do we go from dm to m? What was that? I heard integrate. Yeah, cool. Okay, just checking. Okay, so m is equal to. Oh, why is it purple? The integral of 4.27x plus 2.16 dx. That's going from x is equal to 0 to a length. What's the length? 4.84. Like 5. I think. Cool. Because that was the length that we had over here. All good, guys? Yeah. So then, also for this, by the way, this m, the reason why we can integrate and say that, because it's just the same as that. This is just m. Just adding all the dm's together. So, in this case, m is going to be equal to, I just did it straight away, 2.135 x squared plus 2.16x. So going from 0 to 4.85. We're good for that? I just divided 4. Maybe I should write it down. That's probably much nicer. 4.27 over 2. There we go. Is that all good? Yeah. Integrating, pretty standard. Which is just equal to, and then I sub everything in. The zeros, we just kind of get rid of that whole expression, so we only really need to sub in 4.84. Is going to be 60.6965 ... kilograms. The m is roughly 60.7 kilograms. And yeah, and the rate, yeah, it's kilograms because our units in this question were kilograms per meter cubed. So if it's in grams, you might have to convert. Any questions? All good? Okay. Let's see. Center of mass of the rod. Now, center of mass, you can kind of think of it as like a weighted average, right? Center of mass is like a weighted average. You know, like we have like, if I have like, I don't know, this pen, for example, obviously there's a bit more mass on this side, so the center of mass is like might be towards there. Right? It's just a weighted average. So what we can do, we can say, this is the discrete form, okay? I'm going to write it in a discrete form just to kind of illustrate what I'm trying to say. I is equal to 1 and then for n number of times for mi xi. Basically, so there's a sum of some small mass at a position xi. If you want to decrease, the incremental mass to infinitesimally small, this becomes x center of mass is equal to 1 over m, the integral of x dm. Now, but we also know that, what was that? Oh, I just said COM, yeah. COM. Cool. Sometimes I say CM, I like to say COM. I don't know why. But then we know that dm is equal to lambda dx, right? So I can just sub it straight into there. So this is just equal to 1 over m integral of lambda x dx. Now, the reason why I have to do that is because x is in distance, m is in, you can't integrate the x in the end because mass is a function of distance, and you can't just, treat x as constant here because it's not necessarily. Or with respect to m. Is that making sense? Cool. So then everything's in terms of x. That's cool. So then our integral is going to be going from 0 to our length, which is 4.85. The x center of mass is going to be 1 over m lambda x squared on 2. Going from, oh no, sorry, my bad. Whoops, jumping the gun. So this, remember our expression for lambda was 4.27 x plus 2.16. Then just x dx. And then, is there any more chocolates? Just pass around chocolates, because eat them all. Go to town. 1 over m. The integral now. We got 4.27 x squared plus 2.16x from 0 to 4.85. And then evaluating the integral, you got 4.27 x to the 3 on 3 plus 2.16 on 2x squared, 4.885. Yeah. Subbing stuff into there again, and using our previous question, we had mass is 60.7 kilograms. That's from the previous part. We get a final answer. X center of mass is equal to roughly 3.09 meters. That's, I don't know what, like, if that's the whole thing is like 4.85, 3 is kind of somewhere like there, right? More or less. I don't know. Is that making sense? What do you mean? Because like, it looks a bit different because I've multiplied it all by x. It's not necessarily integrated version. Yeah. Cool. Any questions? Okay, cool. Thanks for coming. If anyone wants to go through that conical pendulum question,
Who's going to stay for the pendulum?
cool.
Can I do it?
Yeah, was it?
Yeah.
Do you want to do it? Okay, cool. I just got to shut off the recording. Okay. And everyone, good luck for the tests. I'll see you later.